Hello everyone, welcome to this presentation. Thank you Professor and all of my class fellow for joining this session. I am Omar Faruk and this is my fourth semester here in Kaun University. Currently I am working as a research assistant under the supervision of Professor J. Young Park, and in this presentation I will cover the third chapter of MMIC technology, and the chapter name is MMIC amplifier. So this is our outline. First we will discuss about DC bias injection, then classical stability and gain analysis. Thirdly we will discuss about noise consideration, and then IF amplifier design, then cascade LNA design. Finally we will discuss about power amplifier design. So first DC injection. DC bias injection. So what is DC bias injection? So mainly for transistor, DC bias is used to operate and set an operating point to show the IV characteristics and the AC microwave signal wings. The IDSS is the saturated drain current and is used as a reference current, and the drain current obtained when the this IDSS obtained when the FET is biased at its specified drain voltage in the zero gate voltage. And the generic FET characteristics is shown in figure, in this figure. Here you can see, you can see 4 point. First point represents the low noise operating point, and then second point represents the FET is operated with VGS close to 0 volt, like here you can see, and ID is close to IDSS. At this bias point, the FET gives its maximum small signal gain. However, the DC power consumption and increase the noise figure tend to make this operating point unattractive. And point 3 is linearity, and this is placed almost exactly in the middle of IB characteristics curve, allowing the maximum linear output power to be achieved for class A operation. And finally, the efficiency point, that is point 4, can be used for a class AB operation of the amplifier for higher efficiency, although the linearity will be degraded. Now the biasing method for FET. So mainly for FET we will use for almost 8 method. From this, here you can see method 1 and method 2. Gradually we will discuss all of that method. And in method 1, the inductor as bias chokes when the drain gate voltage is required to be positive and the gate voltage is required to be negative. It is very convenient to find a topology with shunt inductor through which the bias can be applied. And method 2, high value resistor. In this method, high value resistor are used to apply the bias voltage like this, and except for low noise and high power amplifier, this is very suitable technique for establishing the gate bias because the gate draw no current and the resistor can be used to stabilize the device. So method 3, that means C, is micro strip stub. In this method, short circuit micro strip stub are used, and the short circuit end is grounded like this with a decoupling capacitor so that the DC bias can be applied. And method 4, this is called self biasing, and in this method the self biasing technique is used, enabling the FET to bias from a single power supply rail, and it is particularly very suitable for battery operation, but it has a drawback, that is it removes this useful post fabrication technique mechanism from the amplifier because the bias is fixed. And method 5, that is E, is called active load, and in this method this method is known as active load technique, in which the active load has zero gate source voltage and hence operate at its saturated drain current. Method F, that is called constant current source self bias technique, and in this method the gate of the amplifying FET is set at 0 volt, but its source is raised to a positive DC volt by drain source voltage of the current source FET. Method G is called DC coupling, and in this method level shifting diode are used to lower the DC output voltage of one stage down to the input voltage of the following stage, and this technique is used for DC coupled amplifier. And the final method is method ACE, and it is called a source stabilization method, and in this method a source stabilization resistor can be added to the desired circuit. Generally this method is used as a standard bias configuration. Our next topic is classical stability and gain analysis. So stability condition is mainly divided into two, that is conditional stability and unconditional stability. And the stability of an amplifier is very important consideration in the design and is decided based on the S parameter of the active device as well as matching and termination. And in conditional stability, the total circuit either can be stable or oscillate under any condition. And in unconditional stability, the total circuit does not oscillate. This is the basic difference between conditional and unconditional stability. Our next topic is improving how to improve the stability, and for improving the stability of the circuit we have several methods. From this, first is resistive loading. In this case transistor stability can be improved by adding a small series or large shunt capacitor, like here you can see this series or shunt capacitor. This is series, and here you can see the shunt capacitor to the input or output as shown in this figure. And the designer should ensure the connection of resistor in series or shunt like this. And for feedback method, most amplifier incorporate some form of feedback, as you all knows. Uh, but the theory of negative feedback has been developed by electronic engineer, and feedback can be either negative or positive. When feedback is negative, then we call it degenerative, and when positive, then we call it as regenerative. And the negative feedback is applied to the MMIC amplifier design because this is very useful. And then how can we calculate the power gain? For this we have three equation here you can see. So first, several power gain equation are used in microwave amplifier design, and the transducer power gain GT, the power gain GP, also called as operation power gain, and the available power gain, that is G, are defined where GT equal power delivered to the load and divided by power available from the source, and GP is defined as the ratio between power delivered to the load and power input from the network, and GA is defined as the ratio of power delivered to the network divided by power input from the source. And in the right figure you can see a diagram of microwave amplifier, and several power gain can be expressed in terms of this special sign. Now, noise consideration. The sensitivity of a communication system is mainly limited by noise, so this is very important term to address for any kinds of electronic device like amplifier. So there are several noise, but no one knows about the noise until H. Nyquist and J.B. Johnson is addressed this in their publication. So first noise is thermal noise. A thermally agitated charge carrier in a conductor constitutes a randomly varying current, which gives rise to a random voltage by Ohm's law. In honor of the contribution made by the individual, thermal noise is often called as Johnson noise or less frequently Nyquist noise. So, however, the thermal noise power is exactly proportional to the temperature. If temperature is increased, then thermal noise is also increased. And here you can see an equation that is P Na equal Kt and del F, where K is Boltzmann, T is temperature, and del F is noise bandwidth in hertz over which the measurement is carried out. And a model of noisy resistor is enclosed within the dash box. Here you can see in this figure as a noise voltage generator in series with resistor itself. Then second is short noise. And what is the short noise? The fundamental basis for short noise is the granular nature of the electronic charge. Two conditions must be satisfied for short noise to occur. First one is there must be a direct current flow, and there also must be a potential barrier over which the charge carrier can loop. And the second one is linear resistor do not generate short noise despite the quantized nature of the electronic charge. It is expected that the short noise current should depends on the charge of the electron and the total DC flow and the bandwidth. Third one is flicker noise. The most mysterious types of noise is flicker noise, that is also called pink noise or 1 by F noise. This phenomenon that have no obvious connections such as cell membrane potential, the earth rotation rate, galactic radiation noise, and transistor noise, all fluctuation with a 1 by F factor. And the final noise is popcorn noise, and it is also known as burst noise, beatable noise, and random telegraph signal or RTS. Popcorn noise shares 1 by F noise sensitivity to contamination, and this noise was first observed in point contact diode, but also has been observed in ordinary junction. Some types of resistors and both discrete and integrated circuit junction transistor. Now about amplifier design. So first the IF amplifier design. The broadband IF amplifier has been designed for KU band L and B, and the bandwidth of the amplifier is in the range of 1 to 2 gigahertz. And the main objectives of this design is to achieve gain for the broadband. The main feature of this amplifier are given here, and in right figure you can see a simplified scheme for IF amplifier design. For this we have three main block. One is input matching, then in inter-stage matching and output matching. This three matching is very important for IF amplifier design. So two stars are used in the common emitter configuration for the broadband amplifier. Here you can see to allow for a voltage divider bias and to provide bias point stabilization. Each stage has a resistor with established constant DC in the emitter of the HBT, and in the bias design the current is used to produce the maximum output signal, showing a signal swing at the DC bias point. As a result of loosey matching, the IF amplifier has a higher gain with very good input and output matching. Based on this common emitter topology, which can be used as current amplifier, the base current is given as the input current and the collector current as the output current. The ratio of the current gain is like I collector current divided by base current. And the fabrication and measurement, here you can see two fabrication layout. One is the MMIC IF amplifier 1000 into 1 to 00 micrometer square, and which is proposed by Professor Nam Young Kim. And here you can see a table and that is about the requirements for a broadband IF amplifier. So frequency gain, input return loss, output return loss, flatness, and PIDB is tabulated here. You can see from this table. Now the cascade LNA design. So in right figure you can see an schematic diagram of cascade LNA with image reject notch. So this figure is mainly um, the cascade design of LNA, and the bias circuit of the cascade stage considered R2, R3, Q6, Q7 and Q2, and this configuration allow the Q2 transistor is function both as mirror transistor and as a driver transistor for the cascade LNA. And in this case resistor R2 and R3 are added in the base to isolate the input from the Q6, and the fully integrated series resonator perform the role of the tunable image reject notch filter, which consists of Q3, Q4, Q5, L3, C4 and C5, and then 10 base collector junction diode like this. A capacitor C4 was connected across the base emitter junction of Q3 to improve the linearity and to reduce the coupling between Q tuning and frequency tuning. When Q tuning is performed, the notch frequency is practically unchanged with addition of C4. The resonance frequency of the notch can be given as given by this formula, where C54 is the emitter base capacitance and Q3 of Q3, and CB is the series connection of C5, and etc. And cascade LNA have several advantages, that is a high gain amplification of weak signal with minimal distortion, typically between 20 to 30 dB, and low noise figure, and it have broad bandwidth like coverage across the entire KU band like 20 to 80 gigahertz, and it have some good linearity and low power consumption, that is efficient operation with minimal power uses, and input and output matching ensure impedance matching like for optimal signal transfer and minimal deflection. It has good stability, and this is compact size, that is a small physical footprint suitable for integration into a system like satellites or ground station. Thermal management, effective dissipation of heat to maintain the performance, and robustness and reliability, durable against environment conditions such as temperature variation and radiation. And here a summary of measurement result about that cascade LNA is tabulated here. I just skip these things for time. And finally, power amplifier design. So what is power amplifier? So power amplifier is a system component whose main task is to increase the power level of signal at its input to predefined level. In contrast with low level amplifier, often specified in terms of a small signal gain, the absolute output power level is the main feature of power amplifier. The devices are typically operated under large signal regime and forcing the exploration, non-linear and operating region. And the specification of the output power is higher than 31 dB, and each stage is carried out per cell. The first stage uses mm, f into 2x f into 2 into 20. The second stage is made with 12 transistor, and third stage is configured into 48 cell. And a simple configuration of 3-stage power amplifier is shown in this figure. And basic design of power amplifier. For power amplifier, ultimately the power amplifier can be considered from the energy perspective of as a component converting DC power from the power supply into microwave power driven by an input power. This process is depicted in this figure, where RF input power here, and here DC power PDC, and the output RF power P output. And the effectiveness of this conversion process is usually described in terms of efficiency, which is defined as the ratio between the RF and the RF and the supplied DC power, which is eta equal P out divided by P DC into 100%. And now load pull method. What is load pull method, right? So the load pull method is a technique used to optimize the performance of a power amplifier by varying the load impedance presented to it. Here a brief explanation here. So first is concept. The method involves systematically varying the load impedance seen by the power amplifier procedure using tunable impedance matching network. Defined impedance are presented to the amplifier measurement. For each impedance setting, key performance metrics such as output power, efficiency, gain, and linearity are measured. Optimization. The data collected is used to identify the optimal load impedance that maximizes the desired performance criteria such as maximum output power or efficiency. Finally, the application. This method helps in designing matching network and understanding how the amplifier behaves under different loading conditions, and leading to improved overall performance. Thank you for your attention. Thank you all.